Welcome back, students. We're going to continue talking about limits, and today we're going to approach limits algebraically and learn some different algebraic methods for evaluating limits. And the foundation of all of these methods is a set of rules or properties called the limit laws or limit properties. And they're kind of just the theory behind what allows you to do what you do. I think this is a place where I can save us a little bit of time, so I'm not going to go into detail about the limit laws. You can look at them if you're interested. They're on page 77 in your book, and I've copied that page here. Here's part of it, and the next part. It's probably not going to be super thrilling to read through these, and it might not even make any sense. So what I'll do is I'll just come back to limit laws anytime I think they're a critical piece of what we need to understand, but for now we're just going to move on. So this is notes number 10, and the first thing you always want to do when evaluating a limit algebraically is try direct substitution. And what that means is take the number that x is approaching, in this case for problem number 1, x is approaching 4, substitute it in to the function. The function will be right there, 2x minus 1 in this case. If you can do it, if it gives you a number, the limit is evaluated and you're done. So we can substitute it in. 2 times 4 minus 1 is 7. The answer is 7. It's as simple as that for this problem. Now I thought since we previously looked at numerical ways to evaluate limits, I thought I would show you that when I put the function y equals 2x minus 1 into my calculator, and when I evaluated it for values of x that are getting closer and closer to 4 from the left and closer to 4 from the right, you can see that the y values are getting closer and closer to 7 as we go in from either end. And then also graphically, since last time we talked about limits, we evaluated them graphically as well. I'll show you that when I graphed the line y equals 2x minus 1, as you approach 4 from the left and as you approach 4 from the right, you're getting close to a height of 7. Okay, here's example number 2. Again, evaluate the limit, try direct substitution first. So that means we're going to try just substituting pi into the function, so that would give us the sine of pi. And remember, to find the sine of pi, you can think of your unit circle. Pi radians is 180 degrees, so we're right over here at the point -1, 0. -1 is the cosine, 0 is the sine. So sine of pi is 0. That's just a regular old finite number, so we were able to evaluate that limit. The answer is 0. And here's the numerical verification. As the values of x get closer and closer to pi from the left and from the right, you can see that the values of y are getting closer and closer to 0. 2.7 e negative 6, that scientific notation, which is 2.7 times 10 to the negative 6th, which is 0.000027. Okay, so that's very, very close to 0. And then graphically, here's the sine graph. Here we have pi as our x value, and you can see from the graph that the y values got closer and closer to 0 as x approached pi. And down here at the bottom of the screen, when x is 3.1415927, which is extremely close to pi, we have 5.898 times 10 to the negative 10th power as our y value. Okay, I'm not trying to imply that every time you evaluate a limit, you have to do it in all of these ways. Most of the time, you're just going to do what I did at the beginning, which was plug in the number and get your answer. That's direct substitution. So let's try a few more. Number 3, the limit of the square root of x minus 1 as x approaches 1 from the right. So this one is a one-sided limit. Still, you can just think of yourself as plugging in the number 1. The square root of 1 minus 1 would be the square root of 0, which is 0. We need it to be a number that's slightly more than 1 because you can't take the square root of a negative and get a real output. So think of your x value as very, very close to 1, but ever so slightly more than 1. Still, that just means you're going to have a value that is ever so slightly greater than 0. It's still heading towards 0. Number 4 is another one-sided limit. It's the same function, but this time x is approaching 1 from the left. So maybe we have 0.9, 0.99, 0.9999. Well, we have a problem because 0.999999 minus 1 is negative, and the square root of a negative is undefined, so this limit actually does not exist. So for some functions, you'll be given a one-sided limit on purpose because the other side doesn't exist. It just varies from problem to problem. Now I have a whole group of problems on this one slide, and they're all related in some way. So we'll work through them and I'll talk about the differences between them. So here we have a rational function and we're finding the limit as x approaches 1. Remember, always try direct substitution first. So let's see, we would have 3 times 1 squared minus 4 times 1 plus 2, and that would be 1 over 6 times 1 minus 3, and that would be 3. Well, there's nothing wrong with an answer of 1/3, so direct substitution worked. We just get 1/3. Next one, another rational function, and we're finding the limit as x approaches 2, so let's try direct substitution first. So we would have 2 squared minus 5 times 2 plus 6, so 4 minus 10 plus 6, that's 0. And then on the bottom we have 2 minus 2, which is 0. Okay, 0 over 0 is a big problem. It doesn't mean 0. It doesn't mean undefined. It means indeterminate, which means we haven't figured it out yet. We might be able to figure out an answer. This limit might have a finite answer. We just can't do it by direct substitution. We need another way. So here's another method, and this method you'll be using quite often. Let's try factoring. Let's try factoring the numerator. It factors into x minus 2 times x minus 3, and the denominator is x minus 2. So we can actually cancel the x minus 2's. Remember, what this means is that this rational function has a hole in it at x minus 2. But if we're working on limits, we don't really care if there's a hole there because we're just looking at what the function is doing as we get really, really close to 2, not actually at 2. Okay, once you've canceled, you can try direct substitution again. Now we have 2 minus 3, and that's negative 1. So this limit actually did have a value, and it was negative 1. Let's take a look at number 7. It's another rational function. Let's try direct substitution. 2 squared minus 5 times 2 plus 5 over 2 minus 2. Okay, so that would be 4 minus 10 plus 5. That's negative 1 over 0. Okay, well, what happens if you have 0 on the bottom and not 0 on the top? We saw in the last problem, 0 over 0 is indeterminate, and you find another way to solve the problem. But if you have something else over 0, that means it's undefined. Basically, remember, we're not really at 2, we're just really, really close to 2. So this denominator is not really 0, it's really, really close to 0, meaning it's infinitely small. And if you take negative 1 and you divide it over something infinitely small, you're going to get something infinitely big. Now, depending on what side of 2 we're on, if we're a little bit more than 2 or a little bit less than 2, we might be getting something really, really big infinity or really, really big negative infinity. Either way, it's not finite, so we're just going to say this is undefined. 0 on the bottom, something else on the top, undefined. And now let's take a look at number 8. Okay, another rational function. Let's try direct substitution. 2 squared minus 5 times 2 plus 6 over 2 minus 1. So that would be 0 over 1. Okay, so I mentioned there were going to be connections between these problems. See how in number 6 we had 0 over 0? That meant one thing. In number 7 we had 0 on the bottom. That meant another thing. Number 8 we have 0 on the top. That means something else. What is 0 over 1? It's just 0. 0 over 2? Just 0. 0 over anything non-zero is just 0. And 0 is an answer. So that is our answer to this problem. I'll put it up here. Okay, what I'm going to do next is pause this video and I'm going to make the rest of the lesson part 2. And I believe we have 3 more examples to work through. So stay tuned and we'll get to the rest of the lesson in the next video. Thanks.